In 2017, scientists officially began an ambitious experiment to photograph a black hole for the first time. A network of radio dishes across 4 different continents joined together to form a giant planet-sized observatory known as the Event Horizon Telescope. It set its sights on 2 targets: Sagittarius A star, the supermassive black hole in the heart of our Milky Way, and an even bigger one lurking in M87. With the globe-sized telescope, the EHT should have enough resolution to directly observe the shadow of a black hole's event horizon.
A lot of people wonder, why haven't you released an image yet? There are 3 reasons for that. One is that it took a long time for the data to get here. At each telescope, we record 64 gigabits per second of data. We record throughout the course of a night, so we're talking about several petabytes of data. For the data volumes we're talking about, the internet is insufficient to transport the data. Nothing beats loading up hard drives onto an airplane and shipping them.
And shipping hard drives from telescopes in Chile and the South Pole to data correlators just took months.
A second reason is because we're being very careful on the calibration. We had incredibly sensitive detections on all of our baselines. And that means that we could actually start to see all the little bumps and wiggles that were instrumental in nature rather than from the source. And the third reason is we're just being extra careful. We have internal reviews all the time where one team goes ahead and works with the data, and then people who weren't involved in that can look at the results and say, all right, well, did you think about this? Did you try this?
At this stage of the project, the team has a solid enough data set to start putting together images.
The telescope coverage itself, it doesn't cover all of the planet. So when we actually want to make images, there's an infinite number of possible images can fit our data set. And we need to actually find what is the most likely images for these sources. It's like a detective work.
We actually have 4 different teams of people making images, and they're working blindly. So one team makes an image, a second team makes an image, and then at the end we compare them and say, are these consistent?
But that comes with a whole new set of obstacles.
For our Milky Way black hole, Sagittarius A star, there are actually 2 challenges. What we are expecting to see is the structure or the plasma flow around the black hole is dynamically changing. Another challenge is that because Sagittarius A star is at the center of our galaxy, we are looking through the many spiral arms of our galaxy. That will slightly blur the image of Sagittarius A star. So we also need to mitigate kind of a scattering effect from the interstellar plasma in front of us on the way to the Sagittarius star.
Before we explain what those are, remember, when it comes to imaging a black hole, scientists can't observe it directly. They're looking at the surrounding matter and light that's being pulled by gravity around the black hole's event horizon. You've probably heard this phrase before. It's the ultimate boundary, the place where
nothing, not even light, can escape.
Nothing, not even light, can escape their gravitational pull.
A black hole is a star so massive that not even light can escape from it.
While the teams are still working on images, they have some guesses as to what the finals might look like.
It's like a crescent image. One side is brighter, and there's a shadow, and another side is very faint.
Those images are still preliminary, and they haven't been released yet. But we expect to have a release of the papers and the images in the late winter or early spring of 2019.
Black holes are basic constituents of our universe, and these monsters are the anchor point in virtually every galaxy. Understanding their formation and dynamics could be the ultimate test of Einstein's theory of relativity, which makes 2 key predictions. First, that the gravity of a black hole curves space-time and draws everything towards it. And secondly, that the shadow of the event horizon cast by the accretion disk should be circular. Depending on what the final images look like, we might need to update the law of the cosmos.
My take is that Einstein was probably right. Every time we try to test relativity, relativity passes the test. The image of the black hole could change our conception of relativity, or it could confirm it. So you predict that you will see a circular shadow, and the size of that shadow is predictable from the distance to the source and the mass of the black hole. We could always get unlucky and not see a shadow at all, but I think that the preliminary data tells us there's something there to be seen.